Ocean circulation patterns form a persistent component of the Earth's physical system. Large-scale currents and subsurface flows are organized by gradients in temperature, salinity, and planetary rotation. These patterns remain structured over long temporal scales, linking distant regions through stable, dynamic relationships. Planetary-scale ocean circulation is commonly organized into a limited number of broad groupings that extend across entire basins or encircle the globe. These groupings are identified by spatial continuity and geographic alignment rather than by local variation. Each grouping occupies a persistent position relative to continents and major ocean basins. Subtropical gyre systems form one major grouping and are present in the Pacific, Atlantic, and Indian Oceans. These systems occupy broad mid-latitude regions within each basin. Their outlines are defined by closed basin-scale circulation patterns that remain geographically stable. Northern and southern hemisphere examples are treated as parallel members of the same classification. Subpolar gyre systems constitute a second grouping and occur at higher latitudes within select basins. These groupings are smaller in areal extent than subtropical systems. Their classification reflects their placement nearer to polar regions, rather than differences in internal structure. Each subpolar system is associated with a specific ocean basin. Equatorial current systems form a distinct grouping located near the global equatorial band. These systems extend longitudinally across ocean basins. Their classification is based on zonal alignment rather than rotational form. Atlantic, Pacific, and Indian Ocean equatorial systems are included within the same category. A separate planetary scale grouping is formed by the Antarctic circumpolar current. This system encircles Antarctica without interruption by continental landmasses. It connects multiple ocean basins into a single continuous circulation feature. No equivalent structure exists in the Northern Hemisphere. Deep and surface circulation components are sometimes referenced as vertical groupings at the planetary scale. These references describe broad, depth-based organization rather than specific pathways. Such groupings are used to distinguish large-scale circulation domains without addressing internal exchange. Together, these circulation groupings provide a stable framework for describing global ocean circulation at the largest spatial scale. Basin-scale circulation can be grouped into domains that subdivide each ocean basin into recurring spatial regions. These domains are defined by position relative to basin geometry and continental margins. This matter will follow. The same domain labels are applied across the Atlantic, Pacific, and Indian Ocean basins for consistent classification. A western boundary domain is identified along the western edge of a basin, adjacent to continental coasts on that side. This domain is typically narrow compared with the basin interior. It is commonly associated with named western boundary current systems in each basin. The domain designation is geographic and does not depend on local details. An eastern boundary domain is identified along the eastern edge of a basin, adjacent to continental coasts on that side. This domain is also relatively narrow compared with the basin interior. It is commonly associated with named eastern boundary current systems. The domain designation follows basin orientation rather than any inferred forcing. A basin interior domain is identified across the central open ocean area between boundary domains. This region corresponds to broad circulation patterns, commonly grouped as gyre interiors at the basin scale. The interior domain is treated as a distinct spatial category in most basin descriptions. The interior domain can be applied separately to subtropical and subpolar latitude bands when both are present. An equatorial domain is identified as the low-latitude band that spans the basin in an east-west orientation. This domain is commonly mapped as a continuous strip across the basin, separate from mid-latitude interior areas. Named equatorial current systems are used as references for this domain. A high-latitude domain is identified where basin geometry reaches polar or near-polar regions. This domain can include subpolar gyre areas and associated boundary segments. The domain label is used to group basin-scale circulation features that share high-latitude placement. Atmospheric circulation separation is used to classify large-scale ocean circulation according to position, north or south of the equator. This classification applies across all major ocean basins. It reflects broad spatial organization rather than continuity across latitude bands. Northern Hemisphere circulation domains are identified in the Atlantic and Pacific Oceans. These domains include basin-scale groupings that remain entirely north of the equatorial band. They are labeled independently from their southern counterparts, even when basin geometry is similar. Each domain is treated as a distinct hemispheric category in global circulation descriptions. Southern Hemisphere circulation domains are identified in the Atlantic, Pacific, and Indian Oceans. These domains occupy basin regions south of the equatorial band. They are classified separately from Northern Hemisphere domains, regardless of shared naming conventions. Southern domains are consistently referenced as independent circulation groupings. The equatorial region functions as a boundary between hemispheric classifications. Circulation features, centered on the equator, are not assigned exclusively to either hemisphere. These features are grouped separately when hemispheric separation is applied. This treatment preserves clarity in large-scale classification. The Antarctic circumpolar current occupies a unique position within hemispheric frameworks. It is entirely located in the southern hemisphere. It is not subdivided by basin or latitude bands. Its classification remains singular and hemispherically distinct. Hemispheric separation is also reflected in naming practices for gyres and circulation systems. Northern and southern features, with similar structure, receive parallel names distinguished by hemisphere. This convention supports consistent global mapping. This hemispheric framework provides a stable method for organizing circulation patterns without reference to variability or exchange across boundaries. Latitudinal circulation bands classify large-scale ocean circulation by broad latitude zones that extend across basins. These bands are defined by geographic position rather than basin boundaries. The same band categories are applied globally for consistent spatial grouping. An equatorial band is identified near the latitude of the equator. This band spans ocean basins in an east-west orientation. Circulation features mapped in this band are grouped together, regardless of basin affiliation. The equatorial band is treated as a distinct category in global classifications. Subtropical bands are identified on either side of the equatorial band in both hemispheres. These bands occupy mid-latitude regions within ocean basins. Subtropical circulation features are grouped according to their latitude range, rather than their basin location. Northern and southern subtropical bands are classified separately. Subpolar bands are identified at higher latitudes between subtropical regions and polar areas. These bands are narrower in latitude than subtropical bands. They are present only in basins that extend sufficiently toward higher latitudes. Subpolar bands are recognized as distinct from both subtropical and polar groupings. A polar band is identified at the highest latitudes where ocean coverage persists. This band is most continuous in the southern hemisphere. In the northern hemisphere, it is limited by continental landmasses. Polar circulation features are grouped primarily by latitude placement. Latitudinal bands are used alongside basin and hemispheric classifications. Each band can intersect multiple basins and domains. This framework allows circulation features to be grouped by global position without reference to driving factors or variability. These bands provide a standardized method for organizing circulation patterns across the world ocean. Zonal and meridional flow groupings classify large-scale ocean circulation by dominant geographic orientation. The classification uses directional alignment relative to lines of latitude and longitude. These groupings are applied across basins as a descriptive framework for mapped circulation features. Zonal circulation groupings are identified where flow is organized primarily along an east-west axis. These groupings appear as elongated features that extend across substantial longitudinal ranges. They are most commonly referenced in equatorial regions and in continuous circumpolar structures. Zonal groupings are used when basin-spanning alignment is more informative than rotational form. Meridional circulation groupings are identified where flow is organized, primarily along a north-south axis. These groupings are referenced in basin-scale linkages between lower and higher latitudes. They are also used to describe boundary-aligned structures that run along continental margins. Meridional groupings can be defined within individual basins or across connected basins through passage regions. Some mapped circulation features include both zonal and meridional segments. Meridional group. In such cases, classification can be assigned by the segment that defines the feature's largest spatial extent. A single named feature may be described as zonal in one region and meridional in another region, without implying change. This approach supports stable mapping descriptions. Zonal and meridional groupings are independent of hemispheric categories. They can be applied within subtropical, subpolar, equatorial, and polar latitude bands. They can also be applied within western boundary, eastern boundary, and interior domains. This orientation-based framework provides a concise method for grouping circulation patterns using geometry and geographic alignment alone. Surface and deep circulation categories classify large-scale ocean circulation by vertical position in the water column. This classification separates circulation features by depth range rather than by geographic location. The categories are applied globally across all major ocean basins. Surface circulation categories include circulation features mapped in the upper portion of the ocean. These features are commonly traced using basin-scale patterns that extend across large horizontal distances. Surface categories are used to group named currents and circulation systems that are consistently identified near the ocean's surface. The classification does not specify depth limits with precision and remains descriptive. Deep circulation categories include circulation features mapped at greater depths below the surface layer. These features are identified as large-scale pathways and domains that occupy deep ocean regions across basins. Deep circulation is treated as a distinct category, regardless of horizontal orientation or basin affiliation. The category includes basin-spanning structures, as well as interbasin connections. Some global classifications distinguish an intermediate circulation category between surface and deep groupings. This category is used to reference circulation features that are neither confined to the upper layer nor assigned to the deepest domains. Its usage varies among mapping conventions. The category remains optional within broad classification frameworks. Surface and deep categories are often used alongside basin, hemispheric, and latitudinal groupings. A single circulation feature may be described using both vertical and horizontal classifications at the same time. This approach allows circulation patterns to be organized by multiple spatial attributes without hierarchy. Vertical circulation categories are descriptive and structural in nature. They provide a stable method for grouping circulation features by depth range without reference to formation, maintenance, or change over time. Subtropical gyre systems are persistent, basin-scale surface circulation configurations located in the subtropical latitude ranges of the major oceans. Each system occupies a broad interior region bounded by continental margins and major oceanic boundary zones. Subtropical gyres are commonly mapped as large closed-loop patterns at the surface in plan view. The North Atlantic subtropical gyre is identified as a continuous surface circulation system spanning the central North Atlantic. The North Pacific subtropical gyre is identified as a comparable system spanning the central North Pacific. The South Atlantic subtropical gyre is mapped across the subtropical South Atlantic as a basin-scale loop. The South Pacific subtropical gyre is mapped across the subtropical South Pacific in a similar basin-scale fall. The Indian Ocean subtropical gyre is identified primarily in the southern Indian Ocean as a large interior circulation system. Subtropical gyres are frequently delineated using named current segments along basin margins. Western boundary current regions are associated with the western edges of these systems in standard atlases. Eastern boundary current regions are associated with the eastern edges of these systems in standard atlases. The interior portions of subtropical gyres are treated as distinct circulation domains, separate from boundary-aligned segments. Gyre outlines are commonly presented as stable features in long-term mean surface circulation maps. Each gyre is treated as a coherent regional unit for basin-scale description. The classification remains consistent across cartographic conventions that emphasize surface circulation structure. Subtropical gyre systems are also used as reference domains for comparing surface circulation patterns across ocean basins. Subpolar gyre systems are persistent surface circulation configurations located at higher latitudes between subtropical regions and polar areas. These systems are mapped primarily in the northern hemisphere, where basin geometry allows closed or semi-closed surface circulation patterns to form. Subpolar gyres occupy smaller spatial extents than subtropical gyres and are positioned closer to continental and polar boundaries. The North Atlantic subpolar gyre is identified across the northern Atlantic basin. It is mapped as a large regional surface circulation system extending between North America, Greenland, and Northern Europe. This gyre is commonly represented as a coherent unit in long-term surface circulation atlases. Its boundaries are drawn using recurring surface flow patterns rather than precise coordinates. The North Pacific subpolar gyre is identified across the northern Pacific basin. It occupies the region between Eastern Asia, Alaska, and Western North America. This system is similarly treated as a distinct surface circulation domain in basin-scale classifications. Its mapped extent reflects consistent, large-scale surface organization. Subpolar gyre systems are not typically identified as closed gyres in the southern hemisphere. In southern high latitudes, surface circulation is commonly grouped under circumpolar or zonally continuous categories, instead of basin-specific subpolar gyres. As a result, subpolar gyre classification is largely limited to northern basins. Within circulation frameworks, subpolar gyres are treated as separate from adjacent subtropical gyres. They are also distinguished from polar surface circulation domains. The classification emphasizes geographic placement and persistence in surface maps. Subpolar gyre systems provide a standardized way to describe high-latitude surface circulation patterns at the basin scale without reference to external drivers or short-term variation. Equatorial current bands are persistent surface circulation configurations located near the global equatorial latitude range. These bands extend primarily in an east-west orientation across ocean basins. They are identified as continuous or semi-continuous surface features in long-term circulation maps. In the Atlantic Ocean, equatorial current bands span the basin between the eastern and western boundaries. Multiple named surface currents are commonly grouped within this banded configuration. The band is treated as a unified surface circulation region rather than as isolated segments. In the Pacific Ocean, equatorial current bands extend across a wider longitudinal range than in other basins. This band is represented as a prominent surface circulation feature in basin-scale atlases. Its mapped extent crosses much of the central Pacific without interruption. In the Indian Ocean, equatorial current bands are identified primarily in the central and eastern portions of the basin. The configuration differs in continuity from Atlantic and Pacific examples, but remains classified within the same category. The band is mapped as a recurring surface feature in long-term representations. Equatorial current bands are distinguished from subtropical and subpolar gyre systems by their zonal alignment and latitude placement. They are not treated as closed-loop systems. Their classification is based on spatial orientation and persistence rather than rotational geometry. These bands may include multiple parallel surface flows within the same latitude range. Such flows are grouped together under the equatorial band designation. This approach simplifies global surface circulation classification. Equatorial current bands are used as reference domains in comparative descriptions of surface circulation across basins. The classification emphasizes geographic consistency and long-term surface configuration without reference to short-term change. Western boundary current corridors are persistent surface circulation configurations aligned along the western edges of major ocean basins. These corridors are mapped as narrow, elongated surface pathways that follow continental margins. Later corridors is the press tower. They form a consistent category in long-term surface circulation representations. In the North Atlantic, the western boundary current corridor is traced along the eastern coastline of North America. It is identified as a continuous surface pathway extending from lower to higher latitudes. This corridor is treated as a distinct surface circulation feature in basin-scale atlases. In the North Pacific, a comparable western boundary corridor is mapped along the eastern coastline of Asia. It follows the basin margin over a large latitudinal range. The corridor is classified separately from interior gyre regions and equatorial bands. In the South Atlantic, a western boundary corridor is identified along the eastern margin of South America. It forms part of the surface circulation framework of the Southern Basin. Its mapped position reflects persistent alignment with the continental boundary. In the South Pacific, a western boundary corridor is traced along the eastern margin of Australia. This corridor is included in surface circulation classifications as a stable basin margin feature. It is distinguished from adjacent interior circulation domains. In the Indian Ocean, a western boundary corridor is identified along the eastern margin of Africa. Its representation varies in continuity across mapping conventions. It remains grouped within the same category as other western boundary corridors. Western boundary current corridors are distinguished by their geographic placement rather than by internal characteristics. They are classified independently of zonal bands and gyre interiors. This category provides a standardized way to organize persistent surface circulation features aligned with basin margins. Eastern boundary current zones are persistent surface circulation configurations aligned along the eastern edges of major ocean basins. These zones are mapped as elongated surface regions adjacent to continental margins. They form a distinct category in long-term surface circulation representations. In the North Atlantic, the eastern boundary current zone is identified along the western coastline of Europe and northwestern Africa. It appears as a continuous surface zone extending across a broad latitudinal range. This zone is treated as a coherent surface circulation region in basin-scale atlases. In the North Pacific, an eastern boundary zone is mapped along the western coastline of North America. It follows the basin margin from lower to mid-latitudes. The zone is classified separately from interior gyre regions and equatorial bands. In the South Atlantic, an eastern boundary current zone is identified along the western margin of southern Africa. It is included as a stable surface circulation zone in representations of the southern basin. Its mapped position reflects long-term alignment with the continental boundary. In the South Pacific, an eastern boundary zone is traced along the western margin of South America. This zone is consistently included in surface circulation classifications. It is distinguished from adjacent interior circulation domains. In the Indian Ocean, an eastern boundary current zone is identified along the western margin of Australia. Its representation varies in extent across mapping conventions. It remains grouped within the same category as other eastern boundary zones. Eastern boundary current zones are classified by geographic placement rather than by internal structure. They are treated as surface circulation regions distinct from western boundary corridors. This category provides a standardized method for organizing persistent surface circulation along basin margins. Circumpolar surface flow regions are persistent surface circulation configurations that extend continuously around high southern latitudes. These regions form a global-scale surface circulation category, distinguished by uninterrupted longitudinal extent. Their classification is based on geographic continuity rather than basin enclosure. The primary circumpolar surface flow region encircles Antarctica across the Southern Ocean. This region links the Atlantic, Indian, and Pacific Oceans into a single surface circulation domain. It is mapped as a continuous band that remains unbroken by continental land masses. The circumpolar region is treated as a singular entity in surface circulation atlases. Circumpolar surface flow regions are positioned at latitudes where ocean coverage forms a near-complete ring around the planet. Their outlines are commonly drawn using long-term averaged surface circulation maps. These outlines emphasize spatial persistence rather than precise boundaries. Minor regional deviations do not alter the overall classification. No equivalent circumpolar surface flow region is identified in the Northern Hemisphere. Northern high latitudes are interrupted by continental landmasses that divide surface circulation into basin-specific domains. As a result, circumpolar classification remains exclusive to southern latitudes. Within global surface circulation frameworks, circumpolar regions are distinguished from subpolar gyres and from basin boundary zones. They are also distinguished from equatorial and subtropical bands by latitude placement. The circumpolar category is applied independently of hemispheric subdivision. Circumpolar surface flow regions may be subdivided into sectors for mapping purposes. Such subdivisions follow basin boundaries for reference only. The underlying classification remains a single continuous surface circulation region. This category provides a standardized method for representing surface circulation that spans multiple ocean basins without interruption. Deep basin-scale flow networks are large, persistent circulation structures identified within the deep ocean. These networks extend across major ocean basins and connect distant regions through continuous deep-water pathways. Their classification is based on spatial continuity and basin-scale reach, rather than on vertical exchange or origin. In the Atlantic Ocean, a deep basin-scale network is mapped along the full length of the basin. This network links northern and southern deep ocean regions through a continuous pathway. It is represented in global circulation maps as a coherent, deep structure spanning multiple latitudes. The Atlantic network is treated as a primary reference for deep circulation classification. In the Pacific Ocean, deep basin-scale flow networks occupy extensive interior regions. These networks are broader in horizontal extent than those in the Atlantic. They are mapped as interconnected deep pathways that span much of the basin floor. The Pacific networks are classified as basin-contained, but globally connected through southern high-latitude regions. In the Indian Ocean, deep basin-scale networks are identified as part of a connected deep circulation domain. These networks link the Indian Ocean to adjacent basins through southern routes. They are mapped as continuous deep pathways rather than isolated segments. The Indian Ocean networks are included as integral components of the global deep circulation system. Southern high-latitude regions function as key connectors between basin-scale deep networks. These regions allow deep pathways from multiple basins to be represented as part of a unified global structure. The networks retain basin identities while remaining spatially linked. Deep basin-scale flow networks are distinguished from surface and intermediate circulation categories by depth placement and spatial persistence. They provide a stable framework for organizing deep circulation patterns, without reference to formation processes or temporal change. Intermediate depth circulation layers are recognized components of large-scale ocean circulation, situated between surface and deep domains. These layers occupy broad depth ranges that extend across major ocean basins. Their identification is based on consistent depth placement and lateral continuity, rather than on interaction with other layers. Intermediate circulation layers are mapped as extensive pathways that follow basin geometry. They connect distant regions through laterally continuous structures. These layers are present in the Atlantic, Pacific, and Indian Oceans. Each basin contains intermediate pathways that are treated as part of a global circulation framework. In the Atlantic Ocean, intermediate depth layers extend along the length of the basin. They link low-latitude and high-latitude regions through continuous mid-depth routes. These layers are represented as coherent features in basin-scale circulation charts. Their outlines emphasize horizontal extent rather than vertical limits. In the Pacific Ocean, intermediate circulation layers occupy wide interior regions. They are mapped as expansive zones that span much of the basin area. These layers are classified separately from deeper networks due to their vertical position. They are included as major elements of intermediate circulation structure. In the Indian Ocean, intermediate depth layers form connected pathways that align with basin contours. They link the basin to adjacent regions through southern connections. These layers are mapped as continuous mid-depth features, rather than isolated segments. Intermediate depth circulation layers are often referenced using basin-specific naming conventions. Despite naming differences, they are grouped together based on shared depth range and persistence. This grouping supports consistent global classification. These layers are distinguished from surface and deep circulation categories by vertical placement alone. The classification provides a stable method for organizing mid-depth circulation pathways without reference to formation, drivers, or exchange processes. Inter-basin deep flow connections are recognized pathways that link deep circulation structures across multiple ocean basins. These connections are identified through continuous deep water routes that extend beyond individual basin boundaries. Their classification emphasizes geographic linkage rather than origin or maintenance. The Southern Ocean region functions as a primary interbasin connection zone for deep circulation. Deep pathways originating in the Atlantic, Indian, and Pacific Oceans converge and diverge across southern high latitudes. These routes allow deep circulation networks from separate basins to be mapped as parts of a connected global system. The connections are represented as continuous features in deep circulation charts. A deep connection between the Atlantic and Indian Oceans is identified through southern pathways that bypass continental barriers. This linkage is treated as a stable component of global deep circulation structure. It is mapped independently of intermediate or surface features. The pathway maintains continuity across basin transitions. A deep connection between the Indian and Pacific Oceans is also recognized through southern routes. This connection links deep interior regions of both basins. It is represented as part of a broader circumpolar deep circulation domain. The classification reflects spatial continuity rather than basin-specific naming. Direct deep connections between the Atlantic and Pacific Oceans are limited by continental land masses. Where linkage exists, it is represented indirectly through southern interbasin routes. These indirect connections are included in global mapping frameworks as part of the same connected network. Interbasin deep flow connections are distinct from basin-scale networks confined to a single ocean. They are also distinct from intermediate depth linkages due to depth placement. This category provides a structural method for representing how deep circulation pathways extend across basin boundaries without reference to exchange processes or variability. Abyssal circulation regions are recognized components of deep ocean circulation, occupying the lowest depth ranges of major ocean basins. These regions are identified by persistent circulation patterns that follow basin-scale topography. Their classification is based on depth placement and horizontal extent, rather than on interaction with overlying layers. In the Atlantic Ocean, abyssal circulation regions are mapped along the deep basin floor, from northern to southern latitudes. These regions form continuous deep pathways that align with the elongated basin geometry. They are represented as coherent features in global deep circulation maps. The Atlantic abyssal regions are commonly treated as longitudinally connected domains. In the Pacific Ocean, abyssal circulation regions occupy extensive deep interior areas. These regions span broad horizontal distances across the basin floor. They are mapped as large, laterally continuous zones, rather than narrow pathways. Pacific abyssal regions are classified as basin-contained components of the global deep circulation system. In the Indian Ocean, abyssal circulation regions are identified across deep basin interiors and along connecting routes to southern high latitudes. These regions link the Indian Ocean to adjacent basins at comparable depths. Their mapped structure emphasizes continuity across deep basins rather than confinement to local depressions. Southern high-latitude areas connect abyssal regions from multiple basins into a unified deep circulation framework. These connections allow abyssal regions to be represented as parts of a globally linked system. Basin identities remain distinguishable within this framework. Abyssal circulation regions are distinct from intermediate depth layers due to their deeper vertical position. They are also distinct from basin-scale flow networks that include multiple depth ranges. This category provides a stable method for organizing the deepest circulation patterns without reference to formation, drivers, or temporal change. Polar origin deep circulation zones are classified as deep ocean regions associated with high-latitude source areas. These zones are identified by their geographic association with polar and near-polar regions, rather than by the processes that define them. They form a distinct category within deep circulation structure mapping. In the southern hemisphere, polar origin deep circulation zones are mapped around Antarctica. These zones extend outward from southern high latitudes into the deep interiors of the Atlantic, Indian, and Pacific Oceans. They are represented as extensive deep regions that retain a common polar association across basin boundaries. The zones are treated as continuous elements of the global deep circulation framework. In the Atlantic Ocean, a polar origin deep zone extends northward along the basin floor. This zone maintains spatial continuity from southern high latitudes into the central Atlantic. It is mapped as a recognizable deep region in basin-scale circulation charts. The Atlantic zone is commonly used as a reference example in global classifications. In the Indian and Pacific Oceans, polar origin deep zones are identified as connected deep regions linked to southern high latitudes. These zones occupy large areas of the deep basin interiors. They are mapped as broad, laterally extensive domains rather than narrow pathways. Their classification reflects shared geographic association rather than basin confinement. No equivalent polar origin deep circulation zone is mapped in the Arctic with comparable global reach. Northern high-latitude deep regions are more limited in extent and are treated separately in circulation frameworks. As a result, polar origin classification is dominated by southern hemisphere zones. Polar origin deep circulation zones are distinguished from abyssal regions by geographic association rather than depth alone. They are also distinct from intermediate depth layers due to vertical placement. This category provides a consistent method for organizing deep circulation regions linked to polar areas without reference to formation, drivers, or exchange mechanisms. Pressure unit conventions define standardized ways to report ocean pressure values. These conventions apply across all depth ranges in the global ocean. They ensure consistency between datasets and comparative references. The primary scientific unit for pressure is the Pascal. 1 Pascal equals 1 Newton per square meter. Because ocean pressures are large, derived units are commonly used. Kilopascals are frequently used for shallow and mid-depth reporting. 1 kilopascal equals 1,000 pascals. Megapascals are commonly used for deep and extreme depth values. 1 megapascals equals 1 million pascals. Another widely used unit is the atmosphere. 1 atmosphere corresponds to approximately 101,325 pascals. Atmospheres provide a convenient comparative scale for depth-related pressure. The bar is also used in oceanographic reporting. 1 bar equals exactly 100,000 pascals. In many contexts, bars and atmospheres appear with similar numerical values. Pressure values may also be expressed using pounds per square inch. This unit is less common in scientific oceanography. It appears primarily in engineering or technical references. All pressure units describe the same physical quantity. Differences arise only from numerical scaling and unit definition. Conversion between units follows fixed mathematical relationships. Ocean pressure values are always reported as absolute pressure. The surface atmospheric pressure is included in reported values. Gauge pressure conventions are not used in standard ocean datasets. Depth-related pressure tables typically list values in multiple units. Megapascals, atmospheres, and bars often appear together. This practice supports cross-disciplinary comparison. Pressure unit conventions do not vary by ocean basin. They are independent of geographic location. They apply uniformly from the surface to maximum recorded depths. Standardized units provide a consistent framework for describing vertical pressure distribution. They allow pressure magnitudes to be compared across depth ranges. No additional qualifiers are required beyond unit specification. East-west oriented circulation bands are organizational patterns defined by dominant alignment along lines of latitude. These bands extend primarily in a zonal direction across ocean basins. Classification is based on geometric orientation rather than on transport magnitude or driving factors. Equatorial bands form a prominent east-west category near the global equator. These bands span large longitudinal distances across multiple basins. They are mapped as continuous or segmented zonal features, depending on basin geometry. Their identification relies on consistent latitude placement across charts. Subtropical zonal bands are identified on either side of the equatorial region. These bands extend across basin interiors with elongated east-west outlines. They are distinguished from boundary-aligned features by their central basin position. Northern and southern subtropical bands are catalogued separately by latitude. High-latitude zonal bands are identified where ocean coverage permits extended east-west continuity. In the southern hemisphere, such bands form broad circumpolar-aligned regions. In the northern hemisphere, zonal continuity is interrupted by continental landmasses. Classification reflects these spatial constraints without modification. Some zonal bands intersect multiple basins through open ocean connections. In such cases, the band is treated as a single organizational feature across basin boundaries. Mapping conventions preserve band identity while noting basin transitions. This approach maintains consistency in global representations. East-west-oriented bands can coexist with north-south-oriented segments in the same circulation system. Zonal classification applies when the dominant spatial extent follows latitude. Segment-level orientation does not alter the band-level category. Zonal organization is applied independently of depth classification. It may describe surface, intermediate, or deep pathways. This framework provides a descriptive method for grouping circulation features by longitudinal continuity alone. North-south-oriented circulation pathways are organizational patterns defined by dominant alignment along lines of longitude. These pathways extend primarily across latitude ranges, rather than along them. Same classification is based on geometric orientation and spatial continuity. Meridional pathways are identified in multiple ocean basins where circulation features span broad north-south distances. These pathways connect low-latitude and high-latitude regions through elongated corridors. They are mapped as continuous features that retain orientation across large portions of a basin. Western boundary pathways are frequently represented as north-south-oriented features. Their mapped form follows continental margins over wide latitude ranges. The orientation classification reflects alignment rather than proximity to land. Similar meridional pathways are also recognized within open ocean areas. These pathways cross latitude bands without strict confinement to basin edges. They are represented as interior connections that complement zonal band organization. Their inclusion supports complete longitudinal latitudinal mapping. In the Atlantic Ocean, several major circulation features are categorized as meridional due to basin geometry and longitudinal extent. In the Pacific and Indian Oceans, comparable north-south pathways are mapped where basin shape permits extended latitudinal reach. Each basin is treated independently within the same organizational framework. Some circulation systems include alternating zonal and meridional segments. In such cases, the meridional classification applies to segments where north-south extent dominates. Segment-level classification does not alter system-level naming conventions. North-south-oriented pathways intersect equatorial, subtropical, subpolar, and polar latitude bands. Orientation classification operates independently of latitude-based grouping. It also operates independently of depth-based categories. This framework provides a descriptive method for organizing circulation features by longitudinal alignment alone. A kidney says it excludes transport magnitude and dynamic interpretation. Cross-equatorial circulation structures are organizational patterns defined by continuity across the equatorial latitude. These structures link circulation features located in both hemispheres through direct or indirect pathways. Classification is based on spatial crossing of the equator rather than on intensity or directionality. In the Atlantic Ocean, cross-equatorial structures are identified, where circulation pathways extend from southern to northern latitudes without termination at the equatorial band. These structures are mapped as continuous features in basin-scale representations. They are treated as single entities despite hemispheric transitions. In the Pacific Ocean, cross-equatorial circulation structures span wide longitudinal ranges. These structures connect northern and southern circulation domains through aligned pathways that intersect the equatorial region. Their mapped form emphasizes geometric continuity rather than segment-level orientation. In the Indian Ocean, cross-equatorial structures are identified where basin geometry allows direct linkage between hemispheres. These structures are represented as connected pathways rather than separate hemispheric components. Classification remains consistent even when continuity varies in mapped detail. Cross-equatorial structures can include zonal segments, meridional segments, or combinations of both. The defining attribute is uninterrupted presence across the equatorial latitude. Orientation may change along the pathway without altering classification. This approach supports flexible representation within a fixed organizational category. Some circulation systems are classified as cross-equatorial at one depth range and not at another. Depth-based variation does not alter the surface or pathway level classification when equatorial crossing is maintained. Cross-equatorial designation is applied independently of vertical grouping. These structures intersect equatorial, subtropical, and higher latitude regions. They coexist with hemispheric classifications without replacement. The framework allows circulation features to be grouped by latitudinal continuity alone. Cross-equatorial circulation structures provide a descriptive method for organizing ocean circulation patterns that span hemispheres. The classification excludes transport magnitude, temporal variation, and dynamic interpretation. Mid-latitude circulation alignment refers to organizational patterns of ocean circulation centered between equatorial and high-latitude regions. These alignments are defined by consistent spatial orientation within mid-latitude bands of both hemispheres. Classification is based on latitude placement and directional coherence, rather than on strength or variability. In many basins, mid-latitude circulation features display a dominant zonal alignment across broad interior regions. These features extend along latitude lines for long distances, before changing orientation near basin margins. Their mapping emphasizes continuity within a defined mid-latitude range. Northern and southern mid-latitude alignments are catalogued separately. Meridional alignment is also present within mid-latitude circulation structures. Such alignment appears where pathways connect mid-latitude regions to adjacent lower or higher latitudes. These north-south oriented segments are grouped within mid-latitude alignment when their central extent remains within the mid-latitude band. Orientation may vary along the pathway without altering classification. Mid-latitude alignment commonly intersects basin interiors and boundary regions. Features within this category are not restricted to a single domain type. Interior and margin-adjacent alignments are included under the same organizational framework when latitude placement is consistent. In the Atlantic and Pacific Oceans, mid-latitude alignment is widely represented due to extensive basin width at these latitudes. In the Indian Ocean, mid-latitude alignment is present primarily in the southern portion of the basin. Each basin is treated independently within the same classification logic. Mid-latitude circulation alignment can coexist with zonal, meridional, and cross-equatorial categorizations. The mid-latitude label applies when geographic placement provides the primary organizing reference. This framework supports consistent grouping of circulation features based on latitude-centered orientation alone. High latitude circulation orientation refers to directional organization patterns located near polar and subpolar latitude ranges. These patterns are defined by geographic placement and dominant alignment rather than by transport characteristics. Classification applies separately in northern and southern high-latitude regions. In the southern hemisphere, high-latitude circulation orientation is commonly organized along extended east-west paths. These paths form broad bands that encircle high southern latitudes with minimal interruption by land. Orientation reflects longitudinal continuity across multiple ocean basins. The southern hemisphere pattern is treated as a unified high-latitude alignment category. In the northern hemisphere, high-latitude circulation orientation is more fragmented. Continental landmasses interrupt continuous east-west alignment. As a result, orientation patterns are organized into basin-specific segments rather than continuous bands. Each segment retains a high-latitude classification despite limited longitudinal extent. Meridional orientation is also present at high latitudes. Such orientation appears where circulation pathways extend toward or away from polar regions. These north-south aligned features connect high-latitude areas with adjacent mid-latitude regions. They are included in high-latitude organization when their primary extent remains poleward of mid-latitude boundaries. High-latitude orientation may vary across basins due to differences in basin geometry. The Atlantic, Pacific, and Indian Oceans each display distinct high-latitude alignment patterns. Despite these differences, classification follows the same latitude-based logic. Orientation is assigned by dominant spatial direction at high latitudes. High-latitude circulation orientation intersects with zonal, meridional, and cross-equatorial frameworks. The high-latitude label applies when latitude placement provides the primary organizing reference. This framework allows circulation features to be grouped by polar proximate alignment without reference to rates, gradients, or dynamic drivers. Basin edge flow alignment refers to directional organization patterns that follow the margins of major ocean basins. These alignments are defined by proximity to continental boundaries and by consistent orientation along basin edges. Classification is based on spatial placement rather than on intensity or variability. Along western basin edges, circulation features commonly exhibit strong north-south alignment. These features trace continental margins over broad latitude ranges. Their orientation remains consistent across large sections of the basin boundary. Western edge alignment is treated as a recurring organizational pattern across multiple basins. Along eastern basin edges, circulation features also display persistent boundary-following alignment. These alignments may extend across wide latitude ranges or remain confined to specific segments. The defining attribute is continuity along the basin margin, rather than uniform extent. Eastern edge alignment is classified independently of western edge patterns. Basin edge alignment can occur in both hemispheres. In the Atlantic and Pacific Oceans, clear edge-following structures are identified on opposing sides of each basin. In the Indian Ocean, basin edge alignment is present along continental margins, where basin geometry supports extended boundary-following paths. Each basin is assessed independently, using the same criteria. Some basin edge features include curved segments that shift orientation locally. Classification remains based on overall adherence to the basin margin. Local changes in direction do not alter the basin edge designation, when boundary alignment dominates the spatial pattern. Basin edge alignment may intersect with zonal or meridional organization frameworks. It may also coexist with latitude-based categories such as mid-latitude or high-latitude alignment. The basin edge label applies when margin-following placement provides the primary organizational reference. This framework provides a descriptive method for grouping circulation features that consistently track basin boundaries. It excludes transport magnitude, gradients, and dynamic interpretation. Multi-decadal circulation persistence refers to ocean circulation features that are repeatedly identified across observation records spanning several decades. These features are recognized through consistent spatial placement and recurring geometry in long-term datasets. Classification is based on recurrence rather than on explanation or attribution. Persistent circulation patterns are documented in major ocean basins through repeated mapping efforts. Subtropical gyre systems appear in similar positions across successive decades. Subpolar gyre systems show comparable spatial recurrence where basin geometry permits. These patterns are treated as stable references in large-scale circulation descriptions. Equatorial circulation bands also display multi-decadal persistence. Their zonal alignment and basin-spanning extent are repeatedly represented in long-term surface circulation maps. While local details vary, the overall band structure remains identifiable across time intervals. This supports their classification as persistent features. Boundary-aligned circulation corridors exhibit long-term recurrence along continental margins. Western and eastern boundary zones are mapped in similar locations across decades. Their repeated appearance supports their use as enduring organizational elements in circulation frameworks. At greater depths, basin-scale and interbasin circulation pathways are also recognized for multi-decadal persistence. Deep flow networks appear consistently in reconstructions based on long-term observations. Southern high-latitude connection regions repeatedly link deep pathways across basins. On some, these deep features are included in persistence classifications without reference to variability. Multi-decadal persistence does not imply invariance at all scales. It indicates that a circulation feature remains identifiable despite shorter-term changes. The classification focuses on recognizable structure rather than exact boundaries or magnitude. This persistence framework provides a stable basis for organizing ocean circulation patterns across extended observation periods. It supports comparative description across datasets while excluding trend analysis, causal interpretation, or projection. Recurrent basin-scale patterns refer to large circulation configurations that reappear consistently within individual ocean basins across extended observation periods. These patterns are identified through repeated spatial similarity, rather than through exact boundary matching. Classification focuses on basin-wide geometry and placement. In the Atlantic Ocean, recurrent basin-scale patterns include interior circulation structures that maintain recognizable outlines across decades. These structures occupy similar central basin regions in successive mappings. Their recurrence supports their treatment as stable reference patterns in basin descriptions. In the Pacific Ocean, recurrent patterns are expressed through expansive basin-scale configurations that persist despite differences in mapping resolution. The broad spatial arrangement remains identifiable over time. These patterns are catalogued as enduring features of Pacific circulation organization. In the Indian Ocean, Recurrent basin-scale patterns are identified primarily in the southern and central basin regions. Their recurrence is documented through repeated representation in long-term circulation datasets. These patterns are grouped as basin-scale features, even when local detail varies. Basin-scale recurrence also applies to the relative positioning of interior regions and boundary-aligned zones. The spatial relationship between these components remains consistent across observation periods. This relational stability contributes to basin-scale classification. Recurrent basin-scale patterns are distinguished from short-lived or localized circulation features. They are also distinct from global scale structures that span multiple basins. The defining criterion is repeated recognition within the same basin framework. Recurrence does not require identical shape or extent in every dataset. It requires that a circulation pattern remains identifiable as the same basin-scale feature across time. Classification emphasizes recognizability rather than precision. This framework allows basin-scale circulation organization to be described using long-term recurrence alone. It excludes interpretation of causes, changes, or future behavior. Stable circulation boundaries refer to persistent spatial separations that recur in long-term representations of ocean circulation. These boundaries are recognized where major circulation domains maintain consistent adjacency over extended observation periods. Classification is based on repeated boundary placement rather than on the processes that maintain it. Isn't this bad? At the surface, boundaries between subtropical gyre interiors and adjacent equatorial bands are commonly represented in similar latitude ranges across decades. These separations appear as recurring transitions in basin-scale circulation maps. The boundary concept is used to describe domain limits without specifying sharp edges. Boundaries between subtropical and subpolar gyre systems are also treated as stable in many atlases. New boundaries, their placement is identified through the repeated positioning of each gyre domain at characteristic latitudes. The boundary remains recognizable despite variability in local detail. Along basin margins, stable boundaries separate boundary-aligned corridors from interior circulation domains. Western boundary corridors are consistently mapped as distinct from central basin interiors. Eastern boundary zones are similarly separated from interior regions in long-term depictions. These boundary distinctions persist across multiple mapping conventions. In the Southern Ocean, boundaries associated with circumpolar circulation regions are frequently represented as stable separations between circumpolar domains and adjacent subpolar or basin-specific regions. The recurring placement of these separations supports their classification as stable boundaries. Sector divisions used for reference do not replace the underlying boundary concept. At depth, stable boundaries are recognized between intermediate circulation layers and deeper circulation domains. These separations recur in vertical classification frameworks. They are described as category limits rather than as discrete physical interfaces. Stable circulation boundaries are defined by repeated recognizability in circulation representations. They provide a consistent way to describe how major circulation domains are partitioned over long periods. This framework excludes trend evaluation, causal interpretation, and projection. Observationally consistent flow regions are circulation areas that appear repeatedly across independent observation records and mapping efforts. These regions are identified through agreement in spatial placement rather than through identical shape or magnitude. Classification relies on consistency across datasets collected over extended periods. Surface circulation maps derived from different observational programs commonly depict similar flow regions within the same basins. Subtropical interior regions, equatorial bands, and boundary-aligned zones recur in comparable locations. The repeated appearance of these regions supports their designation as observationally consistent. In the Atlantic Ocean, several surface and deep flow regions are recognizable across ship-based observations, float records, and reanalysis products. Their outlines vary slightly between datasets, yet their central positions remain stable. This consistency allows them to be treated as persistent circulation regions. In the Pacific Ocean, observationally consistent regions are identified across a wider spatial scale. Large interior circulation areas and basin margin zones appear in similar configurations across multiple observational sources. The persistence of these configurations supports basin-scale classification. In the Indian Ocean, observational consistency is observed in both interior and boundary-adjacent regions. Despite differences in data density across time, major circulation regions remain identifiable. Their recurrence across datasets supports inclusion within long-term stability frameworks. At greater depths, observationally consistent flow regions are identified through compiled deep circulation reconstructions. Basin-scale deep regions and interbasin connection zones recur across independent analysis. These deep regions are included based on spatial agreement rather than inferred continuity. Observational consistency does not require perfect alignment between data sets. It requires that a flow region can be recognized as the same circulation feature across multiple records. This framework supports descriptive classification while excluding interpretation of causes, changes, or future behavior. Historical circulation pattern continuity refers to the repeated identification of the same circulation configurations across extended historical records. These records include early observational charts, later instrumental datasets, and modern compilations. Continuity is defined by recognizable similarity rather than by exact replication. Major basin-scale circulation patterns appear consistently across historical mapping efforts. Subtropical gyre systems are depicted in comparable central basin positions in early and later sources. Subpolar gyre systems are similarly represented, where basin geometry allows. These repeated depictions support their classification as continuous historical features. Equatorial circulation bands also display historical continuity. Early oceanographic charts and subsequent datasets place these bands at similar latitude ranges. Their longitudinal extent varies by basin, yet the overall zonal organization remains recognizable. This recurrence supports long-term classification without reference to short-term change. Boundary-aligned circulation features show strong historical continuity along continental margins. Western boundary corridors appear repeatedly along the same basin edges across decades of records. Eastern boundary zones are likewise placed in consistent positions in successive mappings. The persistence of margin-following alignment contributes to historical continuity frameworks. At depth, large-scale circulation structures are identified consistently as observational coverage expanded. Early deep circulation reconstructions and later analyses describe comparable basin scale and interbasin pathways. While detail increases over time, the broad structural layout remains similar. These deep features are included in historical continuity classification. Historical continuity does not imply identical boundaries in all records. It indicates that a circulation pattern remains identifiable as the same structural feature across time. Variations in depiction reflect differences in data resolution rather than replacement of the pattern. This framework allows circulation patterns to be organized using long-term historical recurrence alone. It excludes interpretation of causes, evaluation of change, and projection beyond the observational record. Long-duration circulation reference frameworks are organizational schemes used to describe ocean circulation features that persist across extended observational periods. These frameworks emphasize structural continuity and recognizability rather than temporal detail. They serve as stable reference systems for comparing circulation representations across decades. Global circulation atlases commonly employ reference frameworks that group surface, intermediate, and deep circulation features into recurring categories. Subtropical and subpolar gyre systems are treated as fixed reference domains within these frameworks. Equatorial bands and circumpolar regions are similarly incorporated as enduring elements. Their inclusion reflects repeated identification rather than assumed permanence. Basin-scale reference frameworks organize circulation features according to consistent basin geometry. Interior regions, boundary-aligned zones, and interbasin connections are mapped using stable relational layouts. These layouts recur across successive compilations, even as observational coverage improves. The framework prioritizes relative placement over exact boundaries. At depth, long-duration frameworks include basin-scale deep networks, abyssal regions, and polar-associated domains. These features are represented as interconnected components of a global structure. Their classification remains consistent across historical reconstructions and modern analyses. The framework allows deep circulation to be described using a shared spatial language. Reference frameworks often integrate multiple organizational dimensions. Basin, latitude, orientation, and depth classifications are combined without hierarchy. This layered approach supports comprehensive description while maintaining long-term stability. Each dimension remains interpretable across time. Long-duration circulation reference frameworks do not assert immutability. They provide a consistent descriptive baseline for organizing circulation features that recur across records. The emphasis is on comparability and continuity. These frameworks enable circulation patterns to be discussed using stable spatial references across long observational histories. They exclude evaluation of change, causal attribution, and future projection. Circulation persists as distributed motion within a connected volume. Patterns remain defined by gradients and rotation, without fixed edges. The exchanges continue within the same continuous field.